The outcome that we want to look at is end-to-end flow. So build, OCI, sign, verify, place, and run. Your identity is issued at runtime. Execution is continuously enforced. What this changes is you do not have implicit trust. There's no silent drift. Only verified artifacts run, trust-aware scheduling, and then the trade-offs are it's much more rigid. So you have to have OCI images already built. You have to define all of your policies that you have. The upfront build out of this is more complex. Break glass is much more difficult, but you do end up with strong guarantees. So today I wanted to give an overview of the true cloud sovereignty and what that means. We will do a deep dive into an architecture of what you're able to do around a sovereignty. The stack starts from the hardware level, and then we work all the way up to the top. So what we're going to learn: why current platforms fail under modern workloads, how zero trust applies to Kubernetes, why OCI becomes a control plane, how identity, policy, and placement all connect, and how this enables AI and agentic systems. So on current platforms today, across any of your Kubernetes deployments, oftentimes what we see are that nodes are not trusted by default, that identity is weak or implicit, and we'll dive into that. Artifacts are assumed to be safe by domain, and that Git expresses intent and not runtime enforcement. So where does this break? More than often, it's multi-region trust leakage, supply chain compromise, AR artifacts lack strong runtime provenance, and lateral movement, this is probably the largest failing, is cheap. And we can dive into what that looks like. So what we've done, we've developed a methodology around Cordant Zero Trust architecture. This can be applied to any Kubernetes deployment. The tooling that we're using here is all open source and applicable, whether you're running this with Cordant, with a different distributions, Kubernetes, if you're running this on Azure, AWS, or cloud. And if we look at the slide that we have here, you'll see that at the very top of the top chain element is your trust domain around HSM, so your hardware encryption, coupled with TPM on all of your nodes. And then further along the stack, you have the runtime domain. We're utilizing SPIRE here a lot, MTLS and Kyverno as the enforcement policy. And then your control domain then rests upon two areas: OCI, the open container, which provides a source of truth, commonly now known as Gitless GitOps. So that's the artifacts, your metadata, policies, and provenance. And then couple that with a contract engine that we have inside of Cordant. And then along that line, it allows you to be able to execute in these trusted domains. So what are the outcomes? Only trusted nodes on your workloads. All workloads have verifiable identity, that all artifacts are signed, verified, and have policy enforcement, and fully auditable and observable. The concept that we're defining here is termed trust sharding architecture. So sharding, sharded trust model enables you to do certain things that current architecture does not allow you to do. So the system it's not a cluster. We're not talking about clustered sharding. So the system is not a cluster. Mothership, or your cluster management control plane, is your overall mothership that we term for Cordant. And then that breaks down into regional trust domains. So this is the concept. And within that, you then have child clusters. If you have a sharded region, that has its own independent trust boundary. Federation is explicit and never assumed. So why does sharding exist in this context? Failure containment, identity boundaries, independent attestation, and policy enforcement, and then controlled federation across regions. Guaranteed, you will always have vulnerabilities. There will always be unexpected methods to exploit. So by building an environment where you can actually shard and contain that exploit, this enables this. So here we actually have a diagram that I've put together as best as I can to try and demonstrate what this means. So if you look at the coordinate sharded architecture, you start defining your regions. You'll have region A, region B, region C. Those regions can either be national, so you could have a region that supports France and then another region that supports Japan, or it can be a region as far as how you break areas within your organization. So for example, your all of your banking application side, or one that contains sensitive information on new product development. However that is. Typically, these regions are defined by compliance that you need to enforce within your organization. And if you look at this model here, again, we're replicating, within region A, having an HSM, the TPM, SPIRE, Kyverno. So a federated control plane then feeds the policy distribution, the trust bundle exchange, trust bundle covering here your certificates, your levels of encryption. It ties in the observability and aggregation of observability, and then compliance reporting. What does this gain, right? So again, to sort of reinforce, sharding is isolation. It is not about scaling. It is not scaling an architecture so that you can grow your fleet. That is something that you do in a different context. This is about isolation itself. So here's an example: the coordinate MCM, the multi-cluster management control plane at the very top. It defines what those contracts are that it enforces to all of the different regions. It also controls and manages the policy distribution. We're using Kyverno here. You can obviously use OPA or others. It is also the control plane for observability and the enforcement of compliance. What do you get out of this? You get the global visibility of everything that's aggregated. You get policy sync and enforcement. It is also how you would distribute, and then federated control of what you're able to do. We leverage MTLS for this, and again, examples here: region A, trust domain A; region B, trust domain B; and region C. So the architecture here you can see very clearly defined across a region as a security boundary. This is not a deployment unit itself. All right, so how do we do this? We initiate it at two levels: the root of trust, which is HSM, and then node trust, which we do with TPM. So hardware HSM, this is offline encryption certificate that you would control. So you would generate the root CA, and we typically say hardware backed. As you develop this, you can even use something as simple as some of the YubiKeys or things in that nature. The only job that it does is sign intermediate CAs, and trust originates outside of the cluster, which is required. So this is your root of trust, HSM. And then the node trust we are able to do through TPM. So TPM records, measures boot state. Node proves integrity via attestation. And then the trust state is evaluated. As you develop this yourself, if you need to do this in a lab, you can easily do this with TPM over using an actual hardware-based solution. Also, one of the advantages of being able to do this is that you're able to utilize additional TPM hardware within your environment. So within Kubernetes, as you know, you can very clearly define if a node is able to even spin up based on it passing integrity checks from the TPM. To go in over this again, but you have initially you've got that root of trust, your HSM. So offline, it's hardware backed, it's never exposed. It provides that root CA that you are going to use across the board for this sharding. It is in custody, typically called offline. Signs only intermediate CAs. It's the only thing it will do ever is sign intermediates. And then the trust originates outside of the cluster. So this is all separate from the cluster itself. Combining that with your node trust, so your TPM, so it records the measure of boot state. When you look at most TPM trust, it will record boot state, but it then does not take the next step. So what are those next steps? One, you integrate this into that provenance through an attestation. So TPM quota assigned by hardware. Trust state is evaluated centrally, and only trusted nodes receive identity. So in our example here, we're showing this with SPIRE. Okay, so if you look at the node attestation flow, very important, the node boots, the hardware initiates at the boot process, then TPM measures that boot. So you have your PCRs that you will define, start small and then grow it. So each stage is measured and recorded. That TPM quota is generated. So TPM signs the PCR values that you'll define, and then that gets passed to an attestation that verifies that quota. And then that trust state is assigned. So the node is then classified as trusted or untrusted through labeling, and then that unlocks SPIRE to issue an actual identity for it. So only trusted nodes receive workload identity. What does that outcome look like? Your trusted node, it passes the checks, you get the green light, and if it's untrusted, there's no identity issued. So if you then link that up with that flow of both the TPM and the HSM, now you end up with a root of trust is the flow. Root of trust is created in the HSM. The nodes boot, the TPM is measured, TPM is generated, attestation verifies and validates that quota. Trust state is assigned to the node, and the node is then trusted with SPIRE providing that issue. And this establishes your hardware rooted foundation for everything above. So let's go into this just a little bit more. So that's the first level. You now have, as the system is brought up, it's backed by both your HSM, so your certificates that are being issued, and by TPM. So how do we actually use that so we get somewhere to be able to leverage this inside of a cloud native environment? For that end-to-end trust flow, we'll have SPIFFE and SPIRE. We'll cover how that communication then falls into your MTLS communication across the board, that you'll then be able to take advantage of OCI with SigStore as a control plane, and your gitless ops. So workload identity. So now we're into the next phase, right? Hardware rooted, workload scoped, and short-lived identities that you get through SPIRE. So if you look at the chart, if we start at the top left, the workload starts. So workload is scheduled. The node attestation, the TPM identity is measured, goes through attestation, and at that stage, you now have SPIRE agent that you have on the node. The agent collects attestation, identifies and requests identity from your SPIRE server. SPIRE server in the region now. So now we've gone into the region, validates attestation, issues the SPIRE ID. With that, the short-term X509 is created, and then the MTLS is issued, right? So secure channel. So now you have communications after all of the passes. This is important to note that only until the checks have done, now the node is actually able to do something. So that trust foundation per region has a dedicated CA. So this is a intermittent CA that's issued from the HSM to the MCM, and now you're in the dedicated CA per the region. The trust bundle is delivered. So the way that you actually deliver those CAs, those certificates, is through OCI. So OCI is the delivery mechanism to provide that. And then coupling your OCI image that is signed, you have the node and workstation policies. Kyverno, in our case, is what we use to measure it. And then you couple that with your short-term identities and ability to revoke. So that's your trust foundation per region. And then, as you can see, we have the life cycle here. The most important thing to do here is that the concept is that the identity is issued, you don't configure it. So common practice around how this is done today is that you would configure that trust. Now you don't configure it, you have it issued to you, right? So overall, every workload proves who it is, and every connection proves who the other is. And that's the key concept not to walk away from here, is that instead of when you are looking at a process that's running, a workload that's running on a node, very much it's not what is that process, but who is that process. And then you know that who of that process is able to run because it is contained within an issued identity that you can monitor and manage itself. Okay, so policy as a gate. So policy is a gate, and compliance is a rule. So every request is verified. Only compliant workloads are allowed to run. So this is the next stage of where we're going here. One, at a very, very high level here, if you think about it, we've had HSM and TPM. Then we've gone into how we issue that. So the next phase of this is the policy that controls what you're allowed to do and not allowed to do. So you have that request. There's a controller that submits this request, and that's all goes through your API server. So all requests go through the API. And within that, we leverage the Kyverno admission controller. So this is the policy agent that validates the request against policies and rules that it has issued. We deliver all of those through OCI as well. So what is the verification? What are those verification checks? One, that the source is an OCI registry where we get this. Two, that the image is digest is issued through that. We do the signature verification. It checks for the provenance. The release contracts match what it already knows, that the required labels that are attached to those are valid, so approved, unapproved, that other required labels are present, so region A, region B. Placement constraints, one of the things about the advantage of doing this is you can start actually enforcing placement. I've got a better slide to talk about that further on. Then your namespace, RBAC, and then multi-tenancy. right? So with that, you get the decision of it passes all of the verification checks that we want that the Kyverno policy has, so it's allowed. If it's denied, then that workload can't go any further. And then the next step, if it is allowed, is workload, that the workload is created, runtime pulls artifacts from OCI, and your workload's launched. You continue to do it. However, you can always update policy depending on what you're doing. So continuous reinforcement. We define all of what that OCI is within that Kyverno policy bundles that are delivered through OCI. So these are the constraints. So what are the cluster and organization requirements? What are the coordinate contracts that have to be applied? Rules and standards, so required labels that you've defined that have to be part of it. What exceptions you can have around things like time-bound policy is the one I used here. And then provenance and signature, that it has to have the signature, so SigStore typically is what we're using. So no policy match, no admission, no execution. So you're able to really have a fine-grained control after passing all of the additional steps we covered before. Now this is your next level. So it is the gate. So coupling with that, and I've sort of touched on this a little bit. Maybe I should have moved this earlier in the slide deck, but OCI now serves as your control plane. So this component is the single source of truth. We're leveraging OCI to be able to control the delivery of what you can actually do. So what's inside of that source of truth of OCI? A lot of, if you look at capabilities that are used today with OCI, it typically would be the container image. It could be some of the metadata. It could be Helm charts. These are typical things that we do. But one of the advantages around OCI is that they are immutable. They are version controlled, they are signed, so that there's a level of trust there. So what are we talking about when we talk about expanding what OCI is, and suddenly you have a control plane? So here at the very top, we could talk about workload artifacts. So again, this is what we typically use OCI for today. So Helm charts, your other configs that you would have, the binaries, so those containers. But then included inside of that, you want to have your policy artifacts, so Kyverno policies, what your constraints are, those policies that are coupled specifically to that OCI image, the workload that the OCI is tied against. Then we would have metadata that can then also be used to tie into it. So SBOMs are all verified. You have provenance. You have attestation checks that are required, and then labels and annotations. So all of that type of metadata. Coupling that with trust metadata. So this is the trust bundle that we've touched on briefly, but trust bundles being issued typically by the trust bundle encompasses your root CA, your intermediate CAs. That is what we're covering here about trust metadata. It can have some policy and signatures in there as well. Then you have the contracts that your multi-cluster management at the top has. So what those contracts are, what it can and cannot do. OCI also provides observability artifacts, so your dashboards, your alerts, your rules, telemetry, and then provenance and signatures. So SigStore signatures, SASL signatures, build provenance. This expansion of abilities of what you're able to do with your OCI, in essence, creates a control plane. So it's your single source of truth. And how do we then leverage that? So pull, verify, trust. If we look at when we implement SPIRE for identity, pull SPIRE bundle, issues workload identities. We have MTLS everywhere. All the communication across the board is MTLS. It's able to, it pulls the CA bundles, rotates certificates through OCI. The delivery of your Kyverno policies that you would have, so ability to pull those policies, validates the requests from coordinate your control plane, your multi-cluster control plane. You'll be able to pull the contracts, what those are, evaluate orchestration, and then you have your typical runtime with being having those artifacts present, and then executing only verified content, and then again observability. You define within the OCI those the telemetry that you want, so your dashboards, your schemas, your rules. If you think of OCI now as a system of record, then everything else is a trusted consumer of it. So what are the key benefits? Single source of truth for all artifacts. It's immutable and tamper evident. I wouldn't say tamper resistant. Replicated globally as we're delivering it through OCI. You have a control of your GitOps environment, so how you're doing it, and then designed for security, and it's built for scale. Hence the reason for leveraging OCI, and that it's the control plane. So end to end. So how does that trust flow work? Root of trust, digital identity, number one. Then we get into the runtime verification. So your workload identity and your secure channel communication with MTLS, and then control enforcement, policy verification, the policy decision that then allows for the enforcement. So how does this actually work? We've talked a lot about the theory behind why we're doing it, and then how we get to sovereign environment. So workload placement, and this is where you start seeing this benefit. So the key principles that we want to look at here is that declaration. The declarations drive the placement. You are declaring what those are for you to be able to do it. So workloads declare the trust, the data, and the runtime needs. The identity proves that the runtime trust is there. Leveraging SPIFFE, identity is issued. Policy decides everything on what can and can't be done. Sovereignty is enforced. And so when we speak about sovereignty here, if you remember, we talked about region A, region B, region C. That those are the shards of sovereignty. And then that trust is continuous because you're able to redo it. In this use case here, we've got an example workload, AI inference server. It is trusted. The environment is for production, which is a label. The GPU is true. The data is restricted. The region is EU West. So in our sharding here, we have region EU West, region EU East, and then APAC Southeast. So those are different trust domains that we have established. And so if you look at that type of workflow, you initiate the intent to deploy the workload that we have defined here, which is AI inference. It goes through the policy checks that are required for it to actually run, so that the OCI is signed. It has a release number. Required labels are present that we've defined in there for labels. Is it allowed in the region or not? Do we have the resources limits? Yes or no? Security context, network policy, and image provenance. Very important for you to start thinking about this, and you can define through policy where a workload can be placed, but not only if just on within that region, but you can then become more specific around things like availability for GPUs, for an example. So if you try and deploy it, you don't have the GPU, then it will fail, right? Kyverno validation We then look at what Cordant provides for contract, again, within the multi-cluster management level. So what do we have here? So we get into the contract rules, where it can run. We are defining here region and data sovereignty. We have cluster capabilities and the trust state, and then placement policies and preferences. So we've got the Kyverno validation. We are now following the contracts that it has to follow. And then the scheduler actually can make the determination of what happens, right? So the scheduler is first going to say, it's met all the policies that we need to have. 2, it's the node is it's in the correct pool of trusted nodes defined by labels. We have sufficient capacity. In other words, there are GPU clusters that are available. It is topology aware. And you can also start defining things like cost and efficiency within the contract rules that you're defining within your MCM. From all of that, you are now able to have that workload run. So if we come down here and look at how we've defined these in this example that I've created, we have available targets for the sharded regions and clusters. Again, so we've said here that it's EU West. So for compliance reasons, it has to run in EU West. So it's capable of being able to be deployed there. Region US East, in this case, we'll see that it's not meeting all of the contracts that are required. So in this example, we have 2 areas that I've been able to define. So in one, it fails for capacity, and in the other one, it fails because the GPUs are not available. Then in APAC region, again, we have different capabilities and capabilities that it does. So you'll see that going through when you define this workload, you then pass it through Kyverno, allowing it. Then for Cordant to be able to define those contracts, that scheduling decision is then made. You can see that this workload can only be deployed on the EU West region. And that's by design, so that you can be very specific that your workload will only run on that area, right? So it's eligible, selected, best match. For the next one, you can see for the US, we've defined it's not selected because there's higher latency, lower priority, there's different reasons. And then it is blocked for Southeast. So you're able to really carve out when and how you do it. And then within that region, now it's actually looking for nodes to be able to run that capability. So we are EU West. It then filters down, and we're able to get into specifically where it can run. And I've got several examples here where we have a mix of different types of GPUs or not having GPUs. The first 2, as you can see, everything works. It has the H100, the trust is trusted, it's been attested, capacity is capability there, and we've got the label of GPU is equal to true. And so for the first nodes, it's able to run. Then if you look at the middle node, we'll see that capacity is not there. Everything else would, if capacity becomes available again, then it would become eligible again. But then we have other nodes where things are missing. So for example, in the first case, I just said there's no GPUs on that node, so therefore it would never run there. And on the second example of a no, I have defined that it's the trust is untrusted. You can define within it different levels of trust depending on what you're doing. So now you're able to start a workload and have, through this methodology, placement of that workload as it steps through the start of its journey from being issued, passing your policy, passing your contract rules, getting scheduled, and then going through which regions are available, and then on that, which nodes are available. So what is the benefit of this? The outcome is that with this GPU workload that you've defined at a very top level, that it required the GPU and trusted nodes, that you needed it to, that it had restricted data, so that also enforces when you can, the allowance of it, that it runs only in EU West, that it's compliant with PCI. And so the result is, as you issue this workload, it is able to run where you want it to go, right? So this is trusted action. It's workload placement just by leveraging this methodology that we have. Again, example workloads that we've done here, models are OCI artifacts, they're verified, signed, reproducible, identity governs access, and no uncontrolled model executions are there, right? So agentic workloads can follow the same principle. So they, in this example, it would be able to, it has the same ability where it's dynamically executes the graphs, short-lived, identity per interaction. So this is what we get out of SPIRE and SPIFFE, and static trust models fail. You could not do this outside of applying these rules. This is an agentic version of our enforcement. I think this is likely something that many are going to start to have to implement if you're not already doing it. But then how do you actually control an agentic workflow? So based off of everything we've covered so far, from a request to a result, here are the steps. So the trigger is the user request, user system. It's going to be your agentic harness that's doing it. Triggers the intent. I have an agent that has to go and do some research. That agent, which I've called A here, agent A gets an identity. It's issued with one through SPIRE, receives a short-lived SPIFFE. It then goes through policy and contract checks through Kyverno, validates that it meets all the policies that are required. It then is able to pull. So we've got the pull the tool model from OCI. So required tool or model is pulled from OCI. And we use ORAS to be able to do this, and that the signature, digest, and provenance are verified, so it's able to pull the tools and the model itself. The tool agent is invoked at that stage, so it is now agent A invokes agent B, or the tool that requires those inputs. That then flows into agent B, gets a new identity, so there's a repeat of step 2, and is able to move on from there. The outcome that we want to look at is end-to-end flow. So build, OCI sign, verify, place, and run. Your identity is issued at runtime. Execution is continuously enforced. What this changes is you do not have implicit trust. There's no silent drift. Only verified artifacts run, trust-aware scheduling, and then the trade-offs are it's much more rigid, so you have to have OCI images already built. You have to define all of your policies that you have. The upfront build-out of this is more complex. Break glass is much more difficult, but you do end up with strong guarantees. This slide deck will be posted, and that would conclude what I have for this webinar.